Monte Carlo type estimation generally requires simulating variables that have conform to a normal distribution. So when we're modeling the stock price, the change in the stock price over any given period can be captured by a kind of exponential growth, where the drift is given by mu, which is the difference between the risk-free rate and the dividend yield, and then the that's for a particular time step, and then a shock is introduced, a random shock is introduced, scaled by the standard deviation of the return, and the epsilon represents the shock, and then we scale that also by the square root of the time step, the time period incorporated. Generating epsilon then is generally in Excel something that's relatively easy to do. We could generate epsilon by using rand, okay, which is a random number generator. Random number generator in Excel, its maximum value would be 1, its minimum value 0. When we F9 here, the values update, and when we took an average of this pool of numbers here, the average would be 0.5, and for the small sample 0.6, and there's greater variability in the smaller sample than the large sample, so we can F9, and you can see this small sample gets thrown around a lot. The larger sample sticks more closely to 0.5. If we want to then ensure that this random number conforms to normal distribution, we could take the rand number and then take norm's inverse, and if we examine norm's inverse for a moment, we can see returns the inverse of the standard cumulative distribution. The distribution has a mean of 0 and a standard deviation of 1. So that's kind of the gold standard you want to impose on your simulation, that when you're running the when you're generating the epsilon term, when we generate epsilon, that it has a mean of 0, standard deviation of 1, and an example of that, as we looked at before, was we tried to model this relationship in terms of the stock price, and then when we F9, we can generate a random type of behavior similar to mimicking, in fact, geometric Brownian motion. Okay, so we want to mimic geometric Brownian motion and say that there's these random paths that the stock price can adhere to, and that gives us a way of demonstrating how the stock price changes through time, where the interval is a 12-month period. Okay, so we've this idea of a random, and then norm's inverse. If we norm's inverse, we can see here the function, if we do F9, the mean is 0, standard deviation is 1, and our sample size is sufficiently big that even though each time these numbers are updating, the mean generally is close to 0, standard deviation is equal to 1. Now Box-Muller also provides us with a similar type of way of getting variables that conform to the normal distribution. So when we're trying to generate the epsilon, there's a few ways we can generate the epsilon. One way we can generate the epsilon, the one that we've been using so far, has been to take a norm's inverse, the norm's inverse of a random variable, and that gives us a random shock. But in a good deal of Monte Carlo, people rely on a Box-Muller, particularly when using C++. So we might just have a look at that. So I'll put in some code here for Box-Muller. where I've left a program from Volupta that estimates a Monte Carlo type estimation for options using C++. So if we click on the link here, we should be able to get that piece of code and just have a little look. So this is from the previous video, and we've run a Monte Carlo type estimation. If we run this, what we find is we're outputting a closed form for Black-Scholes call, Black-Scholes put, and also we're getting results from a simulation, and we have 10 million runs. The way we generate the normal variate, right? The way we generate the random shock element, or epsilon, the Z if you like, is we use a box Muller type specification here. So we can take this out and just have a little look at it and go back into Excel for a moment. So let's just copy that, go back into Excel. Notice also, if you want to get this program and code available online, just go to the web link here. Okay, so we'll go back into Excel for a moment, and we just put the specification below, and you can see that we're generating Z using square root -2 times the log. U1 is a random number that's generated. So a rand, R-A-N-D, open bracket, close bracket in Excel. And then we have sine 2 times pi. So pi is our usual pi, 3.14, etc., times another random number. And we can have a look at that here. I've already set up something similar, right, here. So this, setting this out, we have this SQRT, right, just denotes returns the positive square root. Okay, so if we go back into Excel, we're taking the square root of 2 times the natural logarithm of a random number of the random number times sine 2 times pi times the random number, and we can just iterate it. If you just pull that down, you're generating more of these numbers. So I've done a whole lot here. In fact, I've gone down 100,000 times here, 102,933. So there's no particular reason why I selected the number. I just finished there, but it's just a relatively large sample, again, of variables that conform to the normal distribution, so should have a mean of 0, standard deviation of 1. And now, can I demonstrate that? Well, a couple of ways I can demonstrate. One is I can just take the standard deviation of this column, and we can see it's a standard deviation of 1, the mean value close to 0. The maximum value is just over 4, it would appear. The minimum value under 5 for that large sample, and there's 1,010. I count the sample because 102,932 here. Okay, so that's the number of variables we have. Now we could do the same if we, for a moment, if I just delete this column and I pull these back, for instance, right? I'll try that one more time. Pull this back. This is for this column here, and you can see that if I do the norms inverse here, norms inverse rand, I'm pretty much getting the same results. In other words, what norms inverse rand does is equivalent to box Muller. Right? So the variables, this norms inverse rand, if we could look at this for a moment. Norms inverse rand, inverse rand. Right, it has a standard deviation of 1, mean approximately of 0, and again the maximum value range, minimum value range is the same. We can F9 that, F9, and we can look at how those values update as we F9, so no major issues there. Okay, so the norms inverse specification can also be reproduced using the specification for box Muller, and we have two specifications for box Muller, one using sine, the other using cosine. And so the only thing that's changing there between the two is cosine or sine. That's the only thing that we have here that's changing between the two. Can we have a look at the distributional properties then of this range of values? Well, we could take roughly from our different sampling here what's the max and minimum values. For convenience, I assumed -4 was the lowest value, and then the highest value is probably 4.4. And then we put in place here this frequency. We specify the list, the column of variables we want to demonstrate the frequency for, and then we say what bucket the J3 to J47 sets up the buckets. So how many values were beyond -4.4, between 4.4 and 4.2, between 4.2 and -4, and that's what we get here. So even when we F4 again, F9 here, we can see the values are updating, but the bulk of the values are, the bulk of the observations are going to be between 0, this range here. Okay, that's where we're observing the bulk of the values. And once we move away here, either side, we get a decline. We can demonstrate that in a graph. Okay, and the distribution then that we get looks very much like a normal distribution. We can do the same for sine. The distribution we get looks like a normal distribution. We could do one more for norms inverse, just to complete, for completeness, norms inverse rand. Okay, so just look at the distributional qualities again. It should be the same. We take, again, this is relatively arbitrary in some respects, the range of values here, the buckets, because it will differ from time to time, but largely speaking 95% of the time we should be between 1.96 standard deviations and -1.96 standard deviations. So roughly 95% of the time we should be between 2 and -2 standard deviations. We can do the same type of setup here. We can set out the frequency. So basically I can copy this, copy, paste, and then we can say, okay, it's not BB for the normal. The range, the column that I want to incorporate in here is A. So we specify that and return. And so we have frequency and of this column here, which is the norms inverse column, and we have the buckets set out as before. And then to fill in the rest of that frequency distribution, just come down, highlight the cells adjacent to the buckets, come up here to the formula bar, and then Control-Shift-Enter, and that will fill in. And then in terms of just setting out a graph then to observe the distributional properties, we can go into Insert, and we can do charts, and let's take this one here, and this is for the norms inverse. So the distributional properties again look very similar to a normal distribution. So norms inverse distribution. And again,